Alright students, let us discuss optical isomerism today. You know the types of isomerism we have discussed in class 11. So optical isomerism is coming under the category of stereoisomerism. As stereoisomerism are of two types, geometrical and optical. Geometrical we have already discussed earlier. Now we shall be discussing optical isomerism. As the name suggests, optical you understand something to do with light. So there are certain pair of organic compounds. Remember, whenever we talk about isomerism, we always talk about at least two compounds having same molecular formula. And depending on the nature of isomerism, we will understand in what way they differ. So these are pair of organic compounds having same molecular and structural formula, but they behave differently towards light. Such compounds are called optical isomers. So you see, here we have taken a source of light which is having one color. So we call it monochromatic light, that is light of single wavelength or light of single color. Now these arrows which are drawn inside the circle, it means that the light is vibrating in all directions. Now as you know, light when it is passed through prism, the path of the light gets deviated. So here we have a specially designed prism called Nicole Prism. Take care of the spelling, it is not Nickel Prism, it's Nicole Prism. Now the speciality of this prism is it makes the light vibrate only in one direction. So here you can see the arrows are pointing only up and down, that means they are vibrating up and down like this. Okay, this is called polarized light. Now when this polarized light is passed through a compound which we want to study, which is optically active, two things may happen. You may find when the light is coming out, the light may either bend towards right like this. Okay, earlier it was vertical, now it has bent like this, got rotated towards right. If such thing happen, then the solution of optically active compound is called Dextro Rotatory. On the other hand, if the light bends towards left like this, okay, then the solution is called levorotatory. Dextro spelling D-E-X-T-R-O and levo is called L-A-E-V-O. Levorotatory, that means the light got rotated towards left. Dextrorotatory quite often is designated by the symbol small plus or small d, and levorotatory is represented by minus or small l. Okay, so this is what we understand by optical isomerism. That means if one of the compounds out of the two is rotating the light towards right through a certain angle, call it specific angle of rotation, then the other will rotate the light towards the left but through the same angle. Suppose here the degree of rotation is 30 degree plus 30 degree, then this will be minus 30 degree for a pair of isomers. So when a plain polarized monochromatic light is passed through a solution of optically active compound, the light gets rotated through certain angle either towards right or towards left. This phenomenon is called optical activity. Now the pair of optically active isomers rotate the light towards right and left to the same extent. So if one is theta, the other is minus theta. The isomer which rotates the light towards right are called dextrorotatory. As I have mentioned here, dextro is also termed as D and plus. Other one is levo, L or minus. Okay. Now how to know whether a compound is optically active or not? This question was asked this year in the board exam. You see the top compounds which we are talking about, they are having sp3 hybridization. That means the carbon is attached to 4 other atoms through single bond. Now if the groups which are attached to carbon, they are all different. You see I have written different symbols X, Y, P, Q. They are all different. That means the compound doesn't have any symmetry. You cannot divide the molecule into two equal parts by any means. Such compounds are called optically active compounds, and the carbon is called chiral carbon, CHIRAL, not chiral, it's called chiral, or asymmetric carbon, or it is also called stereocenter. Okay, all these terms are used for this particular carbon. So the condition for a compound to be optically active is it should not have any symmetry, should not have any plane of symmetry or point of symmetry, whatever. Now, what should be the relationship between the two optical isomers? That structurally, in what way they should be, what kind of relationship they should possess? As you know, they have same molecular formula, they have same structural formula. Then what is the difference between them? You see, if I assume that I am holding a mirror here, I am holding a mirror and this is the compound. Okay, now the mirror image of this compound will be this. Now remember, these are two different molecules. Okay, but if I lift this particular compound, the left one on the right, they will be non-superimposable. The term is non-superimposable mirror images. Take care, they are not super impossible. They are not superimposable. That means you cannot impose one over the other. It's just like the, as you know, the right hand and the left hand, they can be considered as their mirror images. And you cannot place your right hand over your left hand so that they match exactly each other. So right hand and left hand, they are non-superimposable mirror images. So the same thing when we apply to organic molecules. If two molecules have such relation, the first condition is they should be mirror images. The second condition is the mirror images should be non-superimposable. Say for example, if I take alphabet A, suppose I take alphabet A. The mirror image of alphabet A is also alphabet A. Now if I lift this and place it over here, then they will exactly match each other, isn't it? So they are superimposable. So they will not possess optical activity when it comes to organic compounds. The condition is they should be mirror images, but they should be non-superimposable. So such pair of compounds which are non-superimposable mirror images are called enantiomers. Alright, so enantiomers optical isomers which are non-superimposable mirror images, and they exhibit optical isomerism. That means if this particular compound is rotating the light towards right, if this is rotating towards right, then this will rotate towards left, but through the same angle. And the instrument by which you can study this optical activity is called polarimeter. Okay, so the pair of optical isomers, when equal proportions of D and L, that means dextro and levorotatory compounds, are taken in a solution, equal amount, remember, then the one will rotate the light towards right, the other one will rotate the light towards left, and the final rotation of the solution will be 0. Such a solution is called Racemic mixture. Take care of the spellings. These are new terms to you. The term mixture is called Racemic mixture or Racemic modification. Now if you have one particular compound which is maybe dextro, and after doing some chemical reaction, the mixture which is forming, which is a racemic mixture, then the process is called Rasimization. Okay, all this you will find in your textbook, and they are also written, the enantiomers are also written by these symbols Dl or plus minus. Okay, the process of conversion of one of the enantiomers, as I have already mentioned, to a racemic mixture is called Rasimization. So as I have mentioned here in the note, you can see, please read stereochemical aspect of nucleophilic substitution reaction from your textbook. And in my textbook it is given in page 296 to 299, and please make sure that the page numbers may not tally, but make sure that you go through, find it out from the textbook. Now some examples of optically active compounds. You see butan 2-ol. Now this central carbon where I have put a star mark, that carbon is optically active because you see to carbon 2 what are the groups attached? CH3 written here, OH written here, H written here, and C2H5 or CH2CH3 written here. Now this is one of the isomers. Now you can see I have written or this. That means if you check by chance, if you have a mirror here, don't you think these two compounds are mirror images of each other? But they are non-superimposable. So they are a pair of isomers. So the first condition for compound to be optically active is the carbon should be sp3 hybridized. Second condition, the 4 groups attached to the carbon are all different. Then such compounds are optically active. And what's the relation between optical isomers? They are non-superimposable mirror images. So I have given here some exercise questions and in-text questions to work out. These are very simple, and please solve it and send it to me for corrections.